Yes, Mr. Hisham, can you hear me?
Yes, I can. How are you, Doctor?
Yeah, fine. Tell me, how are you?
Everything is good. Alhamdulillah.
Good, good. So I hope this is your first class, isn't it?
Yes, finally, I managed to know how to, in fact, reach out to the students, and they informed me about the new arrangements,
Okay.
which is good. So, yeah, looking forward to learn much from you, Doctor.
Yeah. Anyway, because we have some time, it is good that we can interact now. So, what is your background?
I'm an industrial engineer,
Industrial
uh,
engineer. Good.
and
Okay.
I worked in the project management with Aramco for
Okay.
about 7 years. And then I joined the government for the local content and government procurement authority
Okay.
for the past almost 2 years and a half.
Good.
And I
Okay.
recently joined a new authority as well, which is the Saudi Exports
Okay.
Development Authority. So this is what I do
Good.
currently. Yeah.
Yeah. Regarding the knowledge of statistics, do you remember anything about statistics?
Yes, we took in the industrial engineering, we took
Sure.
I think 2 or 3 courses.
Yes.
But to be honest with you, it would be very hard to remember now
Yeah.
much of the content. But I am sure that I can refresh my mind once I see the formula or the concept. I can easily and hopefully I will be
Sure.
able to remember the content. Yeah.
Yeah, that is good. Were you able to access to the materials which you have
Uh,
missed for the last three sessions?
Uh, you, in fact, yesterday you were kind enough to reply to me and saying that I can find the previous course, but I couldn't, in fact. I saw the horizontal lines that you said, but I didn't find last session's recording. I think I'm not sure if it was uploaded or not.
No, it was uploaded and it is, I can see that one in my system. It must be there. Maybe we can
So,
ask others also whether they have got any problem. Other than that, I had posted the material for the PowerPoint slides together with the discussion questions with the answers and other files also. Were you able to access them in the course content?
yeah, yeah, yes, yes, the material
Yeah.
where it was, I think, labeled introduction, right?
Yes. Introduction.
Yes,
Then we
yes,
went through probability. Then we went through the probability distributions. Then in the last class, we went through the sampling distributions. So those are the chapters which I think I have missed.
yeah,
Please
yes,
go through them.
yeah,
Yeah.
uh, yes, I am going through them. I have started already. And I
Okay.
was able to find the material and everything is okay in terms of the downloads and stuff.
Okay.
But I'm not
Okay.
sure about the recording for last class. To be honest with you, see
Okay.
now I am doing it with you on my phone. I went to the course, then I went to a course content, right? And then virtual classes, you said,
Don't go to
right?
course content. You just straight away go to virtual classes.
Um,
From
how
where you are
come?
accessing your, from where you are now accessing your online class. Okay.
So I put.
For access, for accessing the online classes, you are making use of the course code. That is the course name QUA 502. So when that
Yeah.
appears, don't go to the virtual class, don't enter into our classroom. Just before entering to the classroom, you will have those 3 lines, and you click on that, you will find the recordings. How about our friends? Mr. Osama, Mr. Saud, can you hear me?
Yes, doctor, can you hear me?
Yeah, sure. So were you able to access the recordings of the last session?
I actually didn't try, but
Okay. What about Mr. Saud?
After I click the 3 lines, what I do?
You look for the recordings. The last, I suppose the last option there.
Okay, clear.
Did you find it, Saud? Because I didn't. And
I think I
find,
have to leave the class before I have to leave
Okay,
the class.
anyway, later on you can do that.
Okay.
Okay. Or maybe during the break, Shasham, you can play that one.
Okay, not a problem. Okay.
Yeah. Anything else would you like to add?
Thank you so much, Doctor.
Okay, welcome, Mr. Mansoor. Yes, any questions from anyone? Osama, Saud, Mansoor? While we wait for others to join. Any questions, please?
well, everything clear, doctor.
Everything clear? Good.
Yes.
What about you, Mr. Saud?
Yeah, I think I have one question
Yes.
in discussion 4, question number 4. It says, what is the probability that the sample is been between 19 and 21? So I have to get the mean, like 20, and work on it.
Not the mean. Is it strictly below, or is it 19 equal to is also there?
No, the sample mean is 20, but I have to get 19 and 21. Between 19 and 21. So I have to work on each of these, or just to get the mean.
I don't have a question with me now. Let me open the question. Okay. Discussion 4.
Discussion 4, yes.
Question 4. Question number
4.
Okay. So suppose a research firm conducted a survey. Okay, sample of 100 steady smokers revealed that sample mean is $20 with standard deviation $5, isn't it? Is this the question?
Yes. Yes.
Okay. So let me share the screen. Can you see the question? Question number 4.
Yes.
So what is the probability that a sample of 100 steady smokers spent between 19 and 21? Okay. So what I want is, I want to calculate the probability of, okay, let me say probability of X to be between 19 and 21. Are you clear?
Yes.
Less than X, less than 21. So this, what I have to do, I have to look for the Z distribution, isn't it? Are you with me?
Yes.
So I have to look for the Z distribution and look for, okay, so let me go back. Writing here may not be easier. Can I write? Okay, insert. Anyway, I will go back to our slides, okay, and then I will try to answer your question, okay.
Okay.
The mean is 20, standard deviation is 5, okay. So between 19 and 21, okay, let me go back. So I have got a normal distribution with mean 20. So I want the probability of
19 and 21.
19 and 21, okay, 19 less than x less than 21. So we have got a distribution where the mean happens to be 20, isn't it?
Yes.
Okay, and the standard deviation happens to be 5.
5.
Okay, this is our sigma. I want the probability of x to lie between 19 and 21. So 19 is somewhere here and 21 is after 20. So I'm looking at this area. Are you with me?
Yes.
So this is the probability I'm interested in with reference to the variable x. So what I do, I convert x into z. Okay. So I look for z distribution where the mean will be 0. And what is the formula for z? Z is given by x minus mu by sigma. Clear?
Yes.
So what is x minus mu by sigma? So what is the point corresponding to, let us say, 19? What will be the corresponding point on z distribution? 19 minus 20 by 5. So 1 by 5. So it will be 0.2, isn't it? Minus 0.2. 19 minus 20 will be minus negative. So it will be minus 0.2 and 21 will be corresponding to plus 0.2. Are you with me?
Yes.
So I am looking for the area between minus 0.2 and plus 0.2 in the Z distribution. So look for your Z table. So open your Z table and look for the value 0.2. So that will give you the area from 0 to 0.2 and take twice of that, you will get the answer.
Okay.
Isn't
So
it?
I add them. I add both of them, minus 2 and 2.
Yeah,
mean the
because
answer?
it is from minus 2 to 0 and 0 to plus 2.
Okay.
So it is a symmetrical distribution. So area from minus 0.2 to 0 is same as 0 to 0.2.
Okay.
So look for the tables, look for the area between 0 to 0.2 and it will be same as this. Both will be equal. So it will take twice the area here, you will get the answer.
Okay.
Is it clear?
Yes, clear. Thank you.
Okay. Any other questions, please?
I have a question, Doctor.
Yeah.
The
Go ahead,
discussion,
Osama.
the discussion number 4 is only for the sampling distribution, right?
Discussion 4, yeah, sampling. Discussion 4
Yeah.
is sampling distribution.
Okay.
Yeah.
Is there any
Is
difference?
it a sampling distribution or? Yeah, okay, sampling distribution.
Okay.
Okay, you're, yes. I have forgotten about the sample size. Mr. Saud,
Yes.
let us go back. It is not, when you are looking at Z, what will be the formula for Z?
Z is x minus mu divided by.
No. What was the question? The question was, what is the probability that a sample of 100 smokers spent between 19 and 21? I am looking for the sample mean. I am looking at the distribution of X bar, a sample of 100 smokers.
Okay, this is sample.
So
Yes.
we are looking for the sampling distribution of the mean. So X bar follows a normal distribution with mean 20 and standard error sigma by root n. Very clear?
Yes. Yes.
So sigma of X bar is sigma by root n. Please make the correction. So this will be X bar minus mu by sigma by root n.
Okay.
This is our Z. So what will be our Z corresponding to this? These two will change. So it will
Okay.
be 19 minus 20 by 5 by 10. Are you clear?
By
1
10,
by
yes.
1 by 0.5. 1 by 0.5 means I think this will be minus 2 and this will be plus 2. So you have to look for the area between minus 2 and plus 2, which is a distribution. Are you clear?
Okay. Okay. Yeah. Now it's clear.
So this is the sampling distribution of the mean, where you are taking a sample of 100 units.
Because it's sample, not population.
It is not population. If you are looking at the population, then you are looking at the distribution of X. Now you are looking at X bar. X
Okay.
bar lying
Yes.
between 19 and 21. Are you clear?
Yes, clear.
Based on the sample of 100 people, we are looking at the mean to fall between 19 and 21.
Okay.
Okay? Yes, Mr.
Okay.
Osama?
Yes, doctor.
Yes. You had any other question?
Yes. Is there any difference if we said, for example, Z area is between more than 5 and less than 10, or more than and equal 5 and less than
No.
or equal 10?
No.
Is it the same?
Because equal to, when a continuous distribution, we are looking at the integration. Integration of, let us say, from 19 to 19 of fx dx. This is nothing but integral. Okay? So at a particular point, if you consider 19, so if you are looking at for a particular point, let us say equal to 19, then this will always be 0. Are you with me?
Yes.
So sigma integral 19 to 19 fx dx is 0 because the lower limit and the upper limit are same.
Are same, yes.
So whether you put equal to or not, it doesn't matter.
It
Probability of
doesn't
x
matter.
equal to 19 or x is equal to a given value is 0 for normal distribution.
So it will be the same.
Same, yes.
Okay,
It
thank you.
doesn't matter. Yes, any other questions, please? And what about the groups for your project? I have not yet received the names of group members in each of the projects. When are you submitting it? I wanted you to do it before today, isn't it?
Yes. We will send you the group names in the WhatsApp group, doctor.
Sure, please do it by
Today,
tomorrow at least. Okay?
Okay.
And let us note that we have got our midterm exam on 9th of October. Okay? There is no change.
Okay.
Exam on 9th October. It will be at the college. Our same room number,
Same classroom, right?
G97. Yeah,
Yes.
same classroom, G97. Okay. So it will be at what time?
6 p.m.
6 p.m. At 6 p.m. Okay. So it will be at 6 p.m. Okay. So it will be for 90 minutes, 6 p.m. to 7:30 p.m. Let us say 90 minutes. The duration will be 90 minutes. Okay, as you know, it carries 30 points. There will be 20 multiple choice questions. and we are including only 3 topics. Chapters 1, 2, 3. Okay. It is introduction, the probability and probability distributions, up to and including normal distribution. So we won't have the sampling distribution. We will have it for, let us say, for final exam, we will have all the chapters. Is it clear?
Yes.
Okay. So shall we continue with our next topic? What is our next topic?
Estimation.
Yeah, estimation and confidence intervals. Okay. What was our previous topic? Shall I take out what is written here? I think I will erase it. Okay.
Okay. So in the last class, we have gone through the sampling distribution of the mean, as I just now told you. We made use of the central limit theorem. Yes.
Sir?
Please go ahead, Mr. Naif.
I have a question in previous slide about the arithmetic mean. About the arithmetic mean and the standard deviation.
X bar, you are looking at the distribution of X bar, isn't it?
Yes, it's the first slide.
Yeah. Okay.
Yeah.
So X bar follows a normal distribution with mean equal to population mean and standard deviation or standard error, which we call it as sigma by root n. Okay.
I do understand it, but I have a question that I didn't know from where did he bring the number. I
Which
don't know if I
number? Can you tell me what was the number? What was the question?
Unfortunately, there is no page number, so I can't tell you what the page number is. But
was it based on the answer which I provided just now for one of the problems where X bar lies between 19 and 21 for the distribution of X bar to be normal? Was it the same question?
No. The question is about it says compute the standard deviation of the vehicle selling prices and the frequency table below. It's just before a topic called relative dispersion, the coefficient of variation.
Was it from the PowerPoint slides?
There is no number slide. There is only
Okay. Is it from PowerPoint? Is it from PPT?
Yes.
Okay. Which chapter?
I have a screenshot. I don't know if I can attach it in the chat or not.
Okay. So can you read the question?
Try to send it in the chat, but.
So can you read the question?
The question says it's an example, not a it's an example, not an exercise. It says
tell me.
Deviation of the vehicle selling prices and the frequency table below. It's before the histogram topic.
Okay, so it should be chapter number 1.
Yes, I think so.
Oh, it should be in introduction. Okay.
Yes, it's an introduction.
So let me try to open that one. I will share the screen. Okay. I will open the chapter number 1, introduction. And I will try to share it. Maybe you will be able to help me out. Okay. Is this the chapter? Before histogram.
Yes,
Here is
before a
some,
histogram.
is it somewhere here?
Yes, this one, the one right below.
Okay. Is it this area, the standard of this second example you are looking at? The standard deviation. Calculation
Yes,
of the
I do
standard deviation? Yeah.
Yes, I understand all of the values, but only the the X bar. I don't know where did he get it from, the number.
X bar is here. The same table on the left side, you have got frequencies and the midpoint. Okay.
Okay.
So what is the formula for mean? It is sigma fm by n. That is, you are multiplying frequency with the midpoint. So that is the third column, fm. Okay.
Okay.
8 multiplied by 16.5 is 132. 23 multiplied by 19.5, like that. Then add them up
So
to get
so it's the same.
1845.
I know how the X bar came from the first example, but I thought it's
Oh
not
no,
the
it
same
is
as
the
the
same
second
example continued. You can see the data. It is the same
okay.
data. Okay.
Okay. والله الفهم. Okay. Thank you so
Very
much.
clear?
I'm sorry. Okay.
Okay.
I
No
got
problem.
it. Yes.
No problem. It
Thank
is the same data. So same example has taken the X bar from the previous calculation.
Okay. Thank
Okay.
you so much. Yes.
Okay. Shall I stop sharing? Okay. Let us go back. Yes. Any other questions, please?
Sorry, doctor.
Any other questions from anybody?
No, thank you. For me, I'm fine. Thank you.
Okay. Okay. So in the last chapter, we have seen that the distribution of X bar follows normal distribution with mean equal to the population mean and standard error sigma by root n, where sigma is our standard deviation for the variable X and n is the sample size. What was the advantage in using the central limit theorem? The advantage is that we are not bothered about the distribution of X. X may be anything. It need not be normal. So it can be any type of distribution you are dealing with. It may be a skewed distribution, it can be multimodal distribution, it can be uniform distribution. It need not be normal distribution. So we are eliminating the necessity for assuming the distribution of X, because most of the situations in reality we don't know the distribution of X. So what we do is we take sufficiently large samples, generally more than 30, and then we know that X bar always follows a normal distribution with mean mu and standard error sigma by root n. So this is the result of the central limit theorem, which has been theoretically proved. So because of this, what we do is now we transform this X bar into Z so that we can make use of the formula for Z, which is X bar minus mu by sigma by root n, which follows a standard normal distribution. Are you clear? X bar minus mu by sigma by root n is a Z variable which follows a standard normal distribution. So we have made use of this particular transformation for arriving at the probabilities. Now we can make use of the Z table or the standard normal table so that we can answer the questions based on the samples. Are you clear? And we have also seen that if sigma is not known, we are making use of a predictor or estimator of sigma, which we call it as S. So the formula becomes X bar minus mu by S by root n, and we have seen that we call it as a T distribution. And T distribution is not one single distribution. We have got a family of T distributions for each sample size, which is defined as the degrees of freedom, where degrees of freedom is given by n minus 1. So we can make use of a t distribution when sigma is unknown. So that we have seen in our last class, isn't it? So we have seen that when sigma is not known, we can make use of the estimator for sigma as mu, as S, and the estimator for x bar is mu. So generally we estimate mu with x bar. X bar is the predictor of mu. X bar is the estimator for mu, and S is the estimator for sigma. And for the proportions, if we are looking at the proportion P, then the sample proportion P cap will be our estimate for P. Are you clear? Are you with me?
Yes.
Yes. So mu, sigma, and P are our parameters, and we are making use of the sample statistic, that is x bar, S, and P cap, which are the statistics. So we are making use of the sample statistic for estimating the population parameter. Now note that we are making use of only one value, one particular value for prediction of or the estimation of mu, sigma, or P. So we call them as point estimates. Point estimates means only one specified value. For mu, we are looking at x bar. Sample mean is a predictor of mu. Now note that x bar depends on our sample. So we are not clear whether we are getting a biased estimate or an unbiased estimate. There may be an error based on the sample we have got. So we are not able to predict the amount of error. Are you clear? So that is one disadvantage of going in for point estimate. If you make use of x bar as the estimate for mu, say for example, we are looking at the average height of a citizen of Saudi Arabia. So based on the sample, I may say that 160 centimeters. I will take a sample of 1,000 citizens, and let us say the samples which I take, they give me all values which are less. Short people may be there, most of the people may be short in my sample. So what happens? The average becomes very low. The value may be just 150 centimeters. Or it may so happen that the people which I have got in the sample may be very tall. So the average may be very high. It may go up to 190 or 200 centimeters. So there may be an error. Are you clear? So the amount of error is not given out, or it is not spelled out by looking at the point estimate. So it will be better for us to have a measure for the amount of error together with the statistic which we are using, the value which we are using for the parameter. Are you with me? Is it clear?
Yes, Doctor.
So we'll look for a interval so that we can get the values for mu to be in an interval. Let us say instead of having the value, let us say if you are looking for the average height of citizen mu, then I may get the value, let us say, as 160 centimeters based on the sample. So instead of 160 centimeter, what I do is I look for a interval, 160 centimeter plus or minus some value. Are you with me? So let us say plus or minus 10 centimeters. So this is the amount of error which I can come across when I am making use of the prediction. In other words, it is in the, well, it will be 160 minus 10 to 160 plus 10. So let us say it will be between 150 and 170. So it is in the interval. So mu lies between 150 and 170 centimeters. But associated with this, we also associate the terminology what is called the level of confidence. In other words, what is the probability that the mu lies within this range? I say that mu lies between 150 and 170. That's right, maybe. But what is the level of accuracy? What is the level of confidence? So associated with this, I will add the level of confidence. It may be 90%, 95%, 80%, 99%, whatever it is. So it is the probability with which mu lies within this range. Very clear? So you are looking for what is called the interval estimate. Is it clear? The difference between point estimate and interval estimation?
Yes, lecturer.
So we are giving an interval so that within this interval, the value of the population parameter will lie associated with that with a given level of confidence. So let us say if I am looking at a level of confidence to be 95%, for example. So it means that 95% of the times I am right to say that the value of mu lies between 150 and 170. So that is the level of confidence. So I can go wrong only 5% of the times. So you can fix your level of confidence and you can say that you can give the interval so that you are sure that the value of mu lies within this interval. It is not only for mu, for sigma and p also, it lies in that interval with a given probability. You will be right 95% of the times. You can go wrong only 5% of the times. So that we call it as the interval estimation. Is it clear to all?
Yes,
Is it clear?
Yes, clear. Yes.
Okay. So if you are looking for the, let us say the interval to be 150 to 170, then what is the width of the, so this we call it as the 160 plus or minus 10, we call it as the confidence interval. We call this as the confidence interval. Confidence interval with a given level of confidence. So let us say the mu lies between 160 plus or minus 10, that is in the interval 150 to 170 centimeters with 95% level of confidence. So what is the width of the confidence interval? What will be the width? Let me say CI. CI means confidence interval. What will be the width of the confidence interval?
20, I believe.
20. In this example, it will be 20, isn't it? So how did you get that? It is nothing but the difference between the upper level and the lower level, or it is nothing but 170 minus 150, so which is 20. Or it is nothing but 2 times 10. Isn't it? It is nothing but 2 times the value plus or minus 10. Are you with me?
Yes.
So this plus or minus 10 is nothing but our error. We call it as the sampling error. Sampling error. Or we can call it as the margin of error. Or it is nothing but your accuracy. You can call it as margin of error, let us say B. Are you with me? So the sampling error or the margin of error or the accuracy of your estimate will be your B. In this case, it will be plus or minus 10. Let us say if your interval was 160 plus or minus 10. So the width of the confidence interval will be nothing but 2 times your margin of error. So it is nothing but your 2B. Very clear? Mansur? So, are you with me?
Yes, clear.
Okay. Now, let us go back. If you look at our Z distribution, so what is the probability that 95 or 90% of the area is within the two limits? Let us say if you are looking at the Z distribution, what are the values, let us say plus or minus Z1, so that the area between the 2 points is 90%. Let us say Z1 plus Z1. So if you take this area as 90% or 0.9, can you tell me what are the values for Z1? You remember? I am looking at 2 points which are equidistant from the mean, which is 0, so that the area between minus Z1 to plus Z1 is 0.90. Yes, Mr. Ahmed.
Yes, we will take as percent of 0.54 or 45, sorry.
Yeah, 45. You look for the area between 0 to Z1, it will be half of 0.9. So it will be something like 0.45, isn't it? So look for your table where the area is 0.45.
Yes.
So can you look at it and tell me what are the values? I think I told you to practice or remember if you want. If the area is 90%, 95%, 99%, generally we'll be coming across. Anybody?
Yeah, it's like 1.64.
Yes, it is 1.645. So 1.64 or 1.65. So in between we can say 1.645. Is it clear? So the area between plus 1.645 and minus 1.645 is 0.90. With me?
Yes.
So probability of, we
Would
can
you
say that.
please, Doctor,
Yes.
would you please, Doctor, explain how did we come up with 1.645?
1.645. Okay. The area from 0 to Z is 0.45. Do you agree? Half of it. We are looking at the symmetry.
Yes, clear.
Okay. So we are looking at 0.45 as the area from 0 to Z, and this is the area given our table. So if you look at our Z table, let me share the Z table. So we are looking at the area 0.45. So look at the body of the table. It gives you the area from 0 to Z. Can you see the table?
Okay. I was able to find it.
Find out.
But
Okay.
these tables will be provided to us, right, in the exam?
Yes, yes. These tables are there. You can make use of the tables in the exam, because the exam will be, okay, for your information, the exam will be using your laptop. You can bring your laptop for the exam. It will be through your LMS. The exam will be available in your LMS, so you can make use of the formulas, you can make use of the tables, you can, or even you can refer to the material which you have got. Okay.
Okay, so it is like an open book, right? Exam.
Almost like an open book, but the time limitation is 90 minutes.
And we need to be in class, right? in the
Yes,
college
you will
itself.
be in class. It will be in class face to face. You can use the computers in the lab, or you can use your laptop if you are comfortable. Okay.
Excellent. Excellent.
So
Thank
we are
you.
looking at this area. This area is given to be 0.45. So we are looking at 0.45, which happens to be between these two values. So 1.6, the second decimal is here, 4 or 5. So you can say 1.645. So that's how we got that. Okay. Is it clear? So that's why we can write that the probability of Z lying between minus 1.645 to plus 1.645 is 0.90. Are you with me?
Yes, doctor.
Now what I do is I replace Z by X bar minus mu by sigma by root n. Okay, let me open another file, share the file so that it will be clear how we got the confidence interval. So let me share this. Can you see this?
Sorry, doctor. Why did we call the half of the length, we called it Z? Why did we call it Z?
Z is actually the standard normal distribution. Z is the transformation
So
we
it's not-
used. Z is the transformation which says that look for your variable X bar, subtract from it the mean and divide by the standard deviation of the variable. So the standard deviation is sigma by root n. So this is the transformation which transforms any distribution of X bar into Z distribution. Z is nothing but a standard normal distribution. Normal distribution with mean 0 and standard deviation 1. Very clear?
Okay,
So
we will
we are using from our
maybe.
last chapter, the result of our last chapter.
Okay, no problem.
Using
Thank
central limit theorem, we have seen that X bar follows a normal distribution with mean mu standard error. We call the standard deviation of X bar is standard error of mean as sigma by root n. Similarly, on the same lines, when you are looking at the distribution of P cap, that is the sample proportion. P cap follows a normal distribution with mean P and standard error of the proportion, that is standard deviation root PQ by n. So those are the results which obtained from our central limit theorem, and we are making use of the same results. Very clear?
Yes.
Okay, please go through them. It becomes more clear. So we have seen that using our Z table, probability of Z lying between plus or minus 1.645 is 0.9. This is from our Z distribution. So what I do, we replace Z by X bar minus mu by sigma by root n. So instead of Z, I will put X bar minus mu by sigma by root n. So X bar minus mu by sigma by root n lies between plus or minus 1.645. Now what I do is I multiply throughout, let us say, by sigma by root n. So it becomes X bar, the minus 1.645 sigma by root n is less than X bar minus mu, which is less than plus 1.645 sigma by root n is equal to 0.9 or 90%. Now I transfer the X bar to both sides, or I add X bar on both sides. So it becomes probability of X bar minus 1.645 sigma by root n to be less than mu to be less than X bar plus 1.645 sigma by root n as 0.9. Are you clear? In other words, the 90% confidence interval for mu will be X bar once I subtract and once I add. So X bar plus or minus 1.645 sigma by root n. So I can say that 90% of the times mu lies between X bar minus 1.645 sigma by root n and X bar plus 1.645 sigma by root n. So this we call it as the 90% confidence interval for the mean mu. Are you with me? Anyway, if you are, don't worry about all this
calculations or how we got it, but this is the result. 90% confidence interval for mu is given by x bar plus or minus 1.645 sigma by root n. And how did we get 1.645? It is based on our 90%. We used our Z table corresponding to 90% or 0.9 and we got 1.645. Are you with me? Abdul Majid?
Yes,
Is it
Doctor.
clear? Yes. So if I change this 90% to 95%, let us say, so what will change? Only this 1.645 will change. Very clear? Only I am changing the area. So for 90%, I looked at the Z table and I got the value to be 1 plus or minus 1.645. Now I am changing the area from 90% to 95%. Only the value of Z will change. So what will be the value of Z? It will be 1.96 from the table. Are you clear? Are you with me?
Yes.
So the formula for 95% confidence interval will be x bar plus or minus 1.96 sigma by root n. Only the number changes. Or if I change it to 99%, again the number changes. The number becomes 2.58 or 2.576, whatever. So 99% confidence interval for mu will be x bar plus or minus 2.58 sigma by root n. So this value only changes if I go on changing my level of confidence. In general, if I call it as 1 minus alpha, let me say this area is 1 minus alpha. So what will be this area and what will be this area? The area above here will be half of alpha, alpha by 2. Are you clear? Because the total area is 1. So 1 minus alpha is the area between minus z to plus z, and the area beyond will be alpha by 2. If you add them, it will be 1. Alpha by 2 plus 1 minus alpha plus alpha by 2. Are you clear? Are you with me?
Yes. Yes.
So this point, let me call it as Z alpha by 2. Z alpha by 2 is the point beyond which the area is alpha by 2. Similarly, on the left, it will be minus Z alpha by 2. The area below minus Z alpha by 2 is alpha by 2. Is it clear? So instead of calling 90 or 95 or 99, I just call it 1 minus alpha. So 1 minus alpha confidence interval for mu is given by x bar plus or minus Z alpha by 2 sigma by root n. Can I say that? In general, I am calling 1 minus alpha. 1 minus alpha instead of 90 or 95 or 99. So in general, I call it as 1 minus alpha. So 1 minus alpha confidence interval, or if you want 1 minus alpha percentage confidence interval for mu is given by x bar plus or minus Z alpha by 2. So these are the points beyond which the area is alpha by 2. So x bar plus or minus Z alpha by 2 sigma by root n. Can I say that? Osama?
I think so, yes.
Yeah. So that's what I do. In general, 1 minus alpha or 1 minus alpha times 100, it becomes percentage. Confidence interval for mu is given by x bar plus or minus Z alpha by 2 sigma by root n. So this is the formula which you must remember, or which is there in your extra formula, or you can make use of it. So the 1 minus alpha confidence interval for mu is given by x bar plus or minus Z alpha by 2 sigma by root n, where Z alpha by 2 is the point beyond which we have got alpha by 2 as the area. Beyond Z alpha by 2, I have got alpha by 2. Below minus Z alpha by 2, I have got alpha by 2. Very clear? This 1 minus alpha, I call it as level of confidence. 1 minus Okay, alpha. I will put it as alpha. 1 minus alpha is called level of confidence. Level of confidence. Okay. Sometimes we can write it as LOS, LOC, level of confidence. And alpha is called the level of significance. Clear? LOS.
Clear.
Please remember that 1 minus alpha is called the level of confidence and alpha is called the level of significance. And what is our sampling error? This Z alpha by 2 sigma by root n is our sampling error. Are you clear? This is our B, the bound of error or the accuracy or sampling error. Are you with me? So Z alpha by 2 sigma by root n is the sampling error. And what is the width of the confidence interval? Width of the confidence interval will be 2 times B. Width of CI. CI means confidence interval will be twice B. 2 times the sampling error. Because it is running from x bar minus B to x bar plus B. So the width will be 2B. Are you with me?
Yes.
Yes, doctor.
So that's what is given. Is this figure clear now? So you are looking at the Z distribution. So you are looking at 1 minus alpha is this area. So this is 1 minus alpha. Okay. So this is the area is alpha by 2 and alpha by 2 on both sides. I have got minus Z alpha by 2 and plus Z alpha by 2. And the 1 minus alpha confidence interval for the mean is given as x bar plus or minus Z alpha by 2 sigma by root n. So this is the result which you must know. So 1 minus alpha is the level of confidence. That is, I am sure that mu lies between x bar plus or minus Z alpha by 2 sigma by root n with probability 1 minus alpha.
Doctor,
Yes.
what we call Z alpha by 2?
Z alpha by 2 is the value of the point beyond which we have got the area to be alpha by 2, which you get from your Z table. This 1.96, 2.58, 1.645, all these are Z alpha by 2. Where in the first case the alpha was 1 minus alpha was 90%. In the second case 1 minus alpha was 95%. So alpha is 5%. In the third case 1 minus alpha was 99%. So alpha is 1%. Are you clear?
Clear.
So in general, the formula for the confidence interval is given by confidence interval for mu is given by x bar plus or minus Z alpha by 2 sigma by root n, where Z alpha by 2 is got from the Z table. And the bound of error is Z alpha by 2 sigma by root n. So note that from x bar it ranges from minus B to plus B. Minus Z alpha by 2 sigma by root n to plus Z alpha by 2 sigma by root n. And the width of the confidence interval is 2 times B. So the width of the confidence interval depends on B. Are you with me? The width of the confidence interval depends on the sampling error. It is nothing but our B, that is Z alpha by 2 sigma by root n. Now, what happens to the width of the confidence interval when we increase our level of confidence, as I increase 1 minus alpha by fixing sigma and n, what happens to the width of the confidence interval? What happens if I increase 1 minus alpha? Let us say if 1 minus alpha was 90%, the value of Z alpha by 2 was 1.645. If I increase from 90 to 95, the value Z alpha by 2 increased from 1.64 to 1.96. Similarly, if I increase from 95 to 99, the value increased from 1.96 to 2.58. So as I increase 1 minus alpha, Z alpha by 2 increases. Are you with me? South?
Yes.
So by fixing sigma and n, as my level of confidence increases, the width of the confidence interval increases because Z alpha by 2 is in the numerator. So as Z alpha by 2 increases, the B value also increases. So 2B also increases. So the width of the confidence interval increases as I increase the level of confidence. Similarly, if I fix the level of confidence and sample size, if I increase sigma, then also the width of the confidence interval increases because sigma is in the numerator. If I fix the variance and the level of confidence, as I increase the sample size, what happens to the width of the confidence interval? As n increases. As n increases, what happens to the width? Hisham?
Would you please repeat the question?
In this, B is Z alpha by 2 sigma by root n. If I fix Z alpha by 2 on sigma and if I increase n, what happens to B?
Would I think would decrease?
It will decrease because n is in this denominator. Very clear? So
Yes.
if we fix the level of confidence and the variance, and if I increase the sample size, the width decreases. So B decreases, so 2 times B also decreases. So these are the changes which take place in the level of confidence or the width of confidence interval as we change each one of them. Changes in the confidence level of confidence, changes in sigma, and changes in n. Are you with me?
So, Doctor,
Yeah.
the more sample we have, the less error we will get, right?
Yes, the less error you are getting. B is small means the sampling error will be less. You are right. Are you clear?
Clear.
Okay, one small variation here will be when sigma is unknown. What happens when sigma is unknown? We replace sigma by S and we replace Z by T. So the confidence interval becomes X bar plus or minus T alpha by 2. Are you clear? T alpha
Yes.
by 2 S by root n. So instead of sigma, I take S and it will be S by root n. Very clear? So this will be the formula for the confidence interval when sigma is unknown. We use the T distribution with n minus 1 degrees of freedom, and we have got separate table and for each of the sample sizes. So for given sample sizes or for given degrees of freedom, for given levels of 1 minus alpha, we have got the table. We can use that for getting the confidence interval for the mean when sigma is unknown. Is it clear?
Doctor, yes. Why we consider 90 and 95? Why don't you, for example, take 70, for example?
You can take any value. Instead of 90, 95, 19. Generally, we look for 90, 95 or 99. You can take any value. Let us say 78%. It doesn't matter. You know how to do that, isn't it?
Yes.
If it is 78%, you take from the table, you get the value of Z. 0.78 divided by 2. You take half of that, it will be let us say 39. So look for the area 0.39 from the table and get the value of Z alpha by 2. So it is exactly same.
Okay, clear.
Are you with me?
Yes, yes, clear.
So whatever is the value of 1 minus alpha, you know how to do it, but the standard values are 90, 95 and 99. These are the standard values. So that if you want, you can remember also, so that you need not go back to your tables. Otherwise, you have to go through the tables and you can get the values. Even if you don't remember, you can use the table and get it. Are you with me?
Yes, yes, clear. Thank you.
Okay. Now, we have seen how to arrive at the confidence intervals for the mean. Similarly, we can get the confidence interval for the proportion. What is the formula you use? There we make use of the transformation. We know that P cap follows a normal distribution, which means P and standard error root PQ by N. So we make use of the information that P cap follows a normal distribution with mean P and standard deviation root PQ by N. So what we do, we look for the confidence interval for the proportion. So the confidence interval for the proportion will be nothing but P cap plus or minus Z alpha by 2 root PQ by N. Because P is not known, we make use of the estimate, we take it as root P cap Q cap by N. P cap Q cap by N. Very clear? So this will be the confidence interval for the proportion, especially when we have NP and NQ to be greater than or equal to 5. We can look for the approximation of the binomial distribution to a normal distribution, and we can make use of our center limit theorem, and the confidence interval for proportion becomes P cap plus or minus Z alpha by 2 root P cap Q cap by N. So this will be the error. This will be our P, the margin of error or the sampling error for proportions. Are you with me?
Yes.
Okay. Now we have seen how to arrive at the confidence intervals. Now I make use of the results of the confidence intervals for determining the sample size. How to find the value of N when we know the level of accuracy to be required and the level of confidence with which we want to determine the sample size, and if we have got an estimate for our standard deviation. In other words, we use the formula B is equal to Z alpha by 2 sigma by root n, isn't it? That is our B. Are you with me? B is Z alpha by 2 sigma by root n. Okay, let me open a blank sheet. Will I take out this? I know that B, that is the margin of error, is Z sigma by root n. Z means that's Z alpha by 2. Okay. So we can call it Z sigma by root n. Are you clear?
Clear.
So now I can take it as B times root n is Z sigma, or N is Z square sigma square by B square, or Z sigma by B whole square. Are you with me? You cross multiply, bring B to the right hand side, it goes to the denominator, square it, you will get N. N is Z square sigma square by B square. So this is the formula we use to determine the minimum required sample size so that you can achieve the given level of accuracy. B is your level of accuracy for a given level of confidence. Z depends on the level of confidence. As your level of confidence increases, let us say Z increases. So you require more number of samples. Similarly, as your accuracy is more, the value of B decreases. You want to have more and more accuracy means the error becomes less. So B decreases. So if you want to have more accuracy in your estimates, then you have to look for N to be larger because B will be smaller and it is in the denominator. So the value of N increases. Are you with me? Is it clear? It's out.
Yes, clear.
So this is the relation between
Yes.
Z sigma B and N. So N is the minimum required sample size so that you can achieve the required accuracy in your estimate for mu at a given level of confidence. So mathematically you can get it. You can calculate the value of sample size. So note that we will look for the minimum number. Means if let us say if the value comes to be let us something like 26.01. We will approximate it to 27. You round it off to the next higher integer. Please remember that. So this is the 26.01 is the minimum required sample size. So because it is the sample size, so the next value could be 27. So any value, don't round it off to the nearest integer, round off to the next higher integer. Are you with me? Is it clear?
So we always
round it to the next higher value. Don't round it off to the nearest value. You take it to the next higher integer.
okay.
So this is the case of mean. So what about the proportion? Similarly, we have got the formula for B. What is B? If you look at the confidence interval for proportion, it gives you B to be equal to Z root PQ by N. Is it clear? So this is the sampling error for the proportions. So once again calculate the value of N. What will you get? Again bring B to the denominator, take N to the numerator and square it. You will get Z square PQ by B square. Are you clear? Let us say P cap Q cap by B square. So this is the formula to calculate your sample size in case of proportions. Are you with me? Is it clear?
Doctor,
Yes.
so in case of large sample size, we will use the
Yeah.
P and Q proportion.
When you are looking at the proportions, when you are trying to, this is for the mean and this is for the proportion. When NP and NQ are greater than or equal to 5, if you have got a binomial situation, when you have got NP to be greater than or equal to 5 and NQ to be greater than or equal to 5, then we can approximate the binomial distribution to a normal distribution. Are you clear? So under these conditions, which most of the situations it will be satisfied, for large sample sizes it will be satisfied. So we can look for the sample size based on the level of confidence and the accuracy levels for proportions also using the formula Z square PQ by B square. I am using the sampling error, that is all. What is B and I am using this for calculating N. So these are the formulae for the sample sizes. Is it clear?
Yes.
Any questions, please? Anybody?
No, thank you, Doctor.
Okay. So these are the things which are given in our slides. So let me go through the slides quickly. With examples, it is there. Estimation and confidence intervals. Can you see the slide?
Yes.
Okay. So as we have seen, a point estimate gives you a single estimate, but we are more interested, it will not give the accuracy of the estimate. What is the error? It will not give. So what we do is we go for the confidence interval or an interval estimate. So the interval estimate gives an interval or range of values which includes the population parameter. So associated with the interval, we have got the level of confidence, the confidence with which the parameter lies within the interval. So a confidence interval or the interval estimate is a range or interval of numbers believed to include an unknown population parameter. Associated with the interval, the measure of confidence, we have that the interval does indeed contain the parameter of interest. So we have got the range of values together with the level of confidence. Okay, as we know, we are making use of the central limit theorem, where we are looking for the sampling distribution of the mean, which is assumed to be normal because of central limit theorem, and the sampling distribution is assumed to be the normal distribution. So we use the property of the central limit theorem, which says that x bar follows a normal distribution with mean mu and standard error sigma by root n, and we have seen that if you look for the 95% level of confidence, that is probability to be 0.95, the formula with the probability of mu lying between x bar plus or minus 1.96 sigma by root n is 0.95. So as the value of 0.95 changes to 90% or 99%, then the constant changes. So in general, we call it as Z alpha by 2. So we call this x bar plus or minus Z sigma. Okay, 1.96 sigma by root n is 95 confidence interval for mu. So this 1.96 is based on 95% confidence level. In general, we have seen how to arrive at that, and this again same thing. 95% of the times the value of will be within the two limits. Okay. So we have seen that for 95% confidence interval, this is the formula for the confidence interval for the mu. This 1.96 depends on your level of confidence. So this 1.96 sigma by root n is often called the margin of error or the sampling error. So please remember these terminologies. Z sigma by root n is called the sampling error or the margin of error. As an example, given the values of n, sigma and x bar, let us say you are given these values. How to calculate the 95% confidence interval for mu? So it is given by x bar plus or minus, if it is 95%, Z is 1.96 sigma by root n. Just substitute the values and simplify, you will get 122 plus or minus 7.84. So the sampling error happens to be 7.84. So once you subtract 7.84 from 122 and once you add 7.84 to 122, you will get the interval between 114.16 to 129.84. So this we call it as the 95% confidence interval for mu. In other words, 95% of the times mu lies between these two values, and the level of the margin of error is 7.84, and the width of the confidence interval is 2 times 7.84. Are you clear? Are you with me?
Yes, clear. Yes.
So this is the general formula for the confidence interval. 1.1 minus alpha or 1 minus alpha % confidence interval for mu is given by x bar plus or minus z alpha by 2 sigma by root n. We call 1 minus alpha is the level of confidence and alpha is called the level of significance. Please remember these terminologies. If 95% level of confidence means 5% level of significance, or 99% level of confidence means 1% level of significance. So in general, for different values of 1 minus alpha, you know how to get Z alpha by 2. For 95%, it is 1.96. For 90%, it is 1.645. For 99%, it is 2.58. For 80%, it is 1.28. So all these values you can always get from your tables. For 98, it is 2.36. Like that. I hope you can get them, isn't it? Are you confident, Mansur? Daud?
Yes, we can get them from the table.
Yes.
Okay, good. For any value of 1 minus alpha, you will be able to get Z alpha by 2. So note that as you change the level of confidence, Z alpha by 2 changes, and as we have seen, as 1 minus alpha increases, Z alpha by 2 increases, so the width of the confidence interval increases. So higher the confidence level, wider is the confidence interval. Similarly, larger the sample size, decreases. So narrower is the confidence interval. So 2 times B also decreases. So if your sample size as n increases, the width of the confidence interval decreases. And as I have told you, when we don't know the sigma, if sigma is unknown, then we replace sigma by S. So we replace it by S and we make use of a T distribution. The formula for T is x bar minus mu by S by root n with n minus 1 degrees of freedom. We have already seen that it is a family of distributions with mean equal to 0 and variance is more than 1. As the degrees of freedom increases, it approaches, the T distribution approaches the Z distribution or standard normal distribution. It is almost very similar to Z distribution. The mean is 0. It is symmetrical, bell shaped. Only thing is it is flatter. So as the degrees of freedom increases, the T distribution approaches the Z distribution. So when sigma is unknown, you replace sigma by S and instead of Z, you make use of T. So that is the formula for our confidence interval. So it will be x bar plus or minus T alpha by 2 S by root n. With n minus 1 degrees of freedom, we look for the T distribution. Are you clear? So we make use of the table of T distributions. We will see how to use that one. So for example, let us look at an example. A stock market analyst wants to estimate the average returns on a certain stock. A random sample of 15 days yields an average annualized return of 10.37% and a sample standard deviation of S, that is 3.5%. Assuming a normal population return, give a 95% confidence interval for the average returns for the stock. So we want 95% confidence interval for mu. So note that here sigma is not known. We are making use of S. S is given. Are you with me?
Yes.
Is it clear? So because sigma is not known, we have to use the T distribution. So the T distribution, we have got n is equal to 15. We are taking sample of size 15. So what will be our degrees of freedom? The degrees of freedom will be n minus 1. So n minus 1 will be 15 minus 1, it will be 14. So to look for 14 degrees of freedom with 95% level of confidence. We are looking for 95% confidence interval. So we have to make use of a T distribution table. So how to make use of T distribution table? Let us see. Let me open the file, T distribution. So we are looking for 14 degrees of freedom. Are you clear? So look for 14 degrees of freedom. So the first column consists of the degrees of freedom. So look for 14 degrees of freedom. And what is level of confidence? The confidence interval? The confidence interval is 95%. So the confidence interval, look for 95% with 14 degrees of freedom. You will get the value as 2.145. Are you with me?
Yes, Doctor, yes.
So this 2.145 is the value of T alpha by 2 for n-1 degrees of freedom, which we use. So let me go back again. So the value happens to be 2.145 from the tables. Is it clear? So that's what we have got. We have used 2.145 from the T distribution tables for 14 degrees of freedom and the 95% level of confidence. So we know the remaining things: x bar plus or minus T alpha by 2 S by root n. X bar value is 10.37. T value we got from the table as 2.145. S is 3.5 and n is 15. So substitute them, simplify, you will get 10.37 plus or minus 1.97. So the sampling error happens to be 1.94. Once you subtract 1.94 for 10.37 and once you add to 10.37, 1.94, you will get the interval as 8.43 to 12.31. Is it clear? How to use T distribution table when sigma is unknown? Yes or no? Are you with me?
Yes, we are with you.
Yes. Okay. Let us look at another example. A manufacturer wishes to investigate the tread life of tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inches of tread remaining with a standard deviation of 0.09 inches. Construct 95% confidence interval for the population mean. So once again, we are looking for the T distribution because you are given the sample mean and sample standard deviation, and our sample size is 10. So exactly similarly, you look for the confidence interval using the T distribution as x bar plus or minus T alpha by 2 S by root n. So here the sample size is 10. So we are looking for the 9 degrees of freedom. So look for degrees of freedom 9 and let us say 95% level of confidence. The value of T you will get it as 2.262. So we will make use of that particular constant 2.262 and use the formula x bar plus or minus 2.262 S by root n. So you'll get 0.32 plus or minus 0.064, which is 0.256 and 0.384. Would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.3 inches? Can you answer this? If you want to give an advertisement that after driving 50,000 miles, so you'll be having the tread to be 0.3 inches. At 95% level of confidence, can you say that? Saud? Mansur, anybody?
Yes.
Yes, you can say 0.30 because the interval is from 0.256 to 0.384. So 95% of the times the tread remaining will be between 0.256 inches to 0.384 inches, and 0.3 is within this range. So I can claim that 95% of the times I am right when I say that the tread remaining will be 0.3 inches because it is within the range of 0.256 to 0.384, which is the 95% confidence interval. Are you with me?
Doctor?
Yes.
Can you please repeat how to read the table regarding
Read the table.
T sigma over 2 n minus 1.
Okay. Yeah. Can you see this table?
Yes.
What is the degrees of freedom? The degrees of freedom is in your first column. Look for the first column, the degrees of freedom. Okay.
Okay.
The degrees of freedom is n minus 1. N is 10. So n minus 1 is 9. Okay.
Okay.
And the level of confidence, the confidence interval is 95%.
95%. Yes.
So look for this column 95%. So 95% column, row is 9 degrees of freedom, the value is 2.262. So that is the value of T alpha by 2, 2.262. Is it clear?
So sigma over 2, we are not consider it in the table.
Which one you are not using? We are using n minus 1 degrees of freedom and T alpha by 2. T alpha by 2, that is we are looking at 1 minus alpha. This is the confidence interval is 1 minus alpha. For various confidence intervals, the values are given. Straight away, he is looking for 1 minus alpha. Are you with me?
Yes, yes.
So this 1 minus alpha is 95% in this example.
Okay.
Is it clear? So I am looking for 95% confidence interval. If I change it to 80%, or then I have to look for this. If it is 99%, I have to look for this. Only the column
Okay,
changes.
Clear, yes.
Clear? Okay. Shall I proceed? Any more questions? So for proportions, we are looking at the distribution of P cap. We know that P cap follows a normal distribution with mean P and standard error root P cube by n. Variance P cube by n or standard error root P cube by n. Because we are looking at the estimates instead of PQ, we use P cap, U cap. So this we can make use of when the NP and NQ are greater than or equal to 5. So we make use of the normal assumption, normality assumption, or normal approximation for the binomial distribution. So the 1 minus alpha confidence interval for the proportion is given by P cap plus or minus Z alpha by 2 root P Q by n or root P cap Q cap by n. So this is the formula which we use for arriving at the confidence interval for the proportion. Anyway, another example. A marketing research firm wants to estimate the share that foreign companies have in the American market for certain products. A random sample of 100 consumers is obtained, and it is found that 34 people in the sample are users of foreign-made products, and the rest are users of domestic products. Are you clear? So we are taking a sample of 100 people. Out of 100 people, 34 people are using the foreign-made products. Give a 95% confidence interval for the share of foreign products in this market. So looking at the proportion, whether they use foreign products or they don't use foreign products. Only two outcomes. So we are taking a sample of 100. Out of 100, 34 people are users of foreign products. So what is P cap? P cap is 34 by 100 or 0.34. Are you clear? So P cap happens to be 0.34. So what is our confidence interval for proportions? It is given by P cap plus or minus Z alpha by 2 root P cap Q cap by n. So substitute the values. P cap is 0.34. Z alpha by 2 is 1.96 because you are looking at the 95% confidence interval from that table. So P cap is 0.34. So Q cap will be 1 minus P cap. So 1 minus 0.34 is 0.66 by n. N is 100. So simplify this, you will get the sampling error, that is 0.34 plus or minus 0.0928. Once you subtract, once you add, so you will get the interval to be 0.24721, 0.4328. Is it clear? Just using the formula.
Any questions?
Clear.
Okay. And next we go for computation of n. We know that if you are looking at the bound of error, using b as x bar, using b as, let us say, z alpha by 2 sigma by root n, that is your b. So use b as z alpha by 2 sigma by root n and get the value of n. So for mean, we get the value of n to be z square sigma square by b square, and similarly for proportions, the value n is given by z square pq by b square. So that is the minimum required sample size. By knowing the accuracy of estimate, the level of confidence, and the estimate for the variance or the estimate for the proportions. So let us look at an example. Yes.
Doctor, in the second formula, why don't we use S instead of BQ?
It is the case of proportions. When you are looking at proportions, you will be looking at the proportion of happenings. You won't get the very, yes, there. You are looking at P and Q, isn't it?
Yes.
You are taking a sample of n, out of n, x are happenings. So the proportion will be x by n. That's how you will have the data.
Okay, so there is no S in that.
We don't use yes. We use, it is the approximation for binomial distribution. For binomial, we look for a proportion only.
Okay.
X happenings out of n trials. Are you clear?
Yes, clear.
So application of the formula in case of mean. Let us say a market research firm wants to conduct a survey to estimate the average amount spent on entertainment by each person visiting a popular resort. The people who plan to survey would like to determine the average amount spent by all people visiting the resort to within $120. So this is the amount of accuracy. Are you clear? With 95% level of confidence. So this is your B, $120. This is the amount of accuracy you want, and this is 1 minus alpha, 95% level of confidence. From the past operation of the result, an estimate of standard deviation is obtained as $400. What is the minimum required sample size? So what is the minimum required sample size? So that you can estimate the amount spent for entertainment to be within plus or minus $120. So n is given by z square sigma square by b square, because it is 95%, z is 1.96, sigma is 400, and level of accuracy is 120. Put the values, simplify, you will get 42.68. So the next higher integer is 43. Round up to the next higher integer. So you have to take a minimum of 43 samples so that you can estimate the amount spent to be within plus or minus $120 with 95% level of confidence. Are you clear?
I get one question.
Yes, please.
How did you know that B is 120, or how did you correspond between the 120 and the B? So what is the indicator?
The indicator is the level of accuracy, the bound of error. The amount of error, what is B? X bar plus or minus Z sigma by root n. So Z sigma by root n is my B. Do you remember? Mu lies between X bar minus B and X bar plus B. So B is the amount of error or the accuracy.
So you are saying.
So here, what is the question? The people who plan to survey would like to determine the average amount spent by all people visiting the resort within $120. Within $120 means they are spending something, let us say some X bar value plus or minus 120. Are you clear? So it should be within $120 on both sides.
Okay, so our interval is from 0 to 120, right?
Yes. Yeah, the accuracy will be between 0 to 120. The maximum error is up to 120, plus or minus 120 on both sides. Here.
Okay, thank you.
So that is my B. So this is my B. That I am getting from the question, it is given. And I make use of the formula for n and I calculate the value of n. So if I had to take a minimum of 43 samples to determine the amount of spent by people on entertainment. Okay. So similarly, we can make use of the formula for the proportions for getting the value of n. The manufacturer of a sports car wants to estimate the proportion of people in a given income bracket who are interested in the model. The company wants to know the population proportion, that is P, within 0.01 with 99% confidence. The current company records indicate that the proportion may be around 0.25. So what is the minimum required sample size? So once again, make use of the formula. We are making use of 99% level of confidence. So the value of Z becomes 2.576 or 2.58. So Z square PQ, P is 0.25. So that is the estimate given. Q is 1 minus 0.25 by B square. B is 0.01. There is something wrong here. It is not this. It will be 0.01 square. Are you clear? Please make the correction. The value of B is 0.01, within 0.01. So 2.576 times 0.25 times 0.75 divided by 0.01 square. So then check for the value, you will get the value. Check for, if there may be some error. If it has taken 0.10, there may be some error. B is 0.01. So calculate it, round it off to the next higher integer. You will get the minimum required sample size. Is it clear? Any questions, please?
Doctor, can you repeat, please, this example?
The manufacturer of a sports car wants to estimate the proportion of people in a given income bracket who are interested in the model. I am interested in the proportion of people. Are you with me?
Yes.
The company wants to know the proportion to within 0.01. So this is the amount of accuracy. So this is the value of B, 0.01. Within 0.01 with 99% level of confidence. So 1 minus alpha is 99%. Current company records indicate that the proportion P may be around 0.25. So the value of P is given. What is the minimum required sample size? So the minimum required sample size, this is case of proportions. The formula is Z square PQ by B square. The value of Z depends on 1 minus alpha. Here it is 99%, so it is 2.576. So 2.576 square times P. P is given to be 0.25. So Q is 1 minus P. So 0.25 into 0.75 by B square. B is 0.01. So 0.01 square.
Okay, okay.
So simplify and see what is the correct answer. I don't know whether this calculation is right or wrong. So simplify and round off to the next higher integer. Is it clear?
Clear.
So this is about the confidence intervals and determining the sample sizes in case of the mean and proportions. This completes our chapter on estimation and confidence interval. Next, we will go to the testing of hypothesis. Before that, any questions? Or do you need any break? Can you hear me?
Yes.
Do you need any break?
I
Saul,
think
I think no need.
Mansur, Hisham. If you want, we can take 10 minutes break and then continue. Shall we do that?
sure.
It's
Okay. So now it is 5:40. So we'll start again at 5:50 after 10 minutes.
550. Okay.
We'll start with hypothesis testing. Okay, we'll meet at 5:50.
Hello.
Okay, are we back? Are we back? Mr. Osama, Saud, Mansur, Naif.
Yes, yes, Doctor.
Yes.
Okay.
Yes, Doctor.
Okay, let us now look at the testing of hypothesis. What is a hypothesis? Anybody?
Experiment,
Experiment,
testing,
testing. We are testing. Testing what? Testing the hypothesis. What is hypothesis?
Assumption.
Assumption, a statement. Just a statement, isn't it? Hypothesis is nothing but a statement. Statement about what? Statement about population parameter. With me?
yes.
So when we are making a statement about population parameter, then we call it as a hypothesis. If it is about a sample statistics, then it is not. So for example, if you are having, let us say, a small shop, and let us assume that the average daily sales is about, let us say, the normal sales is about $100. So then if you make a statement that the mean daily sales, let us say mu, is $100, then it is a statement about the population parameter. Are you with me? Whereas this is a hypothesis. Whereas if you say that I take a sample of, let us say, 30 days, and if I say that the average daily sales is $300 or $30 or $100, whatever it is, then is this a hypothesis? This is not a hypothesis because it is a statement about the statistic. So a statement about population parameter is called hypothesis. Are you clear? So X bar is 300 is not a hypothesis. P is 0.2, it is a hypothesis. Whereas P cap is 0.3, it is not a hypothesis. Are you with me? Is it clear?
Clear, yes.
So if we make a statement about the population parameter, then we call it as hypothesis. So when we have got a hypothesis, the hypothesis can be that there is a situation, let us say our daily sales happens to be about $100, any given value. It can be $1,000 or there are 1,000 customers who are visiting our, let us say, hospital every day. So mu is equal to 1,000. Or let us say the average income of an MBA graduate is 20,000 real. So mu is equal to 20,000. So mu is a given value in general. So when you say that you are having a statement about mu, then it is a hypothesis. Are you with me?
Yes.
Okay.
Yes, Doctor.
Now let us say, for example, let us say we have got a situation where the daily sales of your shop is about $100. Let us say it is $100. So this is about the statement about your population parameter, that is our mean. So the normal average happens to be $100. Now as the manager of the shop or as the owner of the shop, you may feel that the average daily sales is increasing nowadays. Are you with me? It is more than $100. Or you may feel that, based on your perceptions, you may feel that the average daily sales has gone down. Means it may be less than $100. Are you with me? So
you may feel that the average daily sales has gone up, means it may be more than $100, or you may feel that it has gone down, isn't it? In that case, it becomes mu is less than $100. Or you may feel that it is not 100, it is different from 100. It has changed. You don't know. In any case, it is not 100. It is different from 100. Are you with me?
Yes.
So these are the three situations you may come across. Any one of them. You will not come across all the three at a time. In one particular situation, you will come across one of these three situations. Are you clear? So you want to carry out a test to see whether the hypothesis that mu is 100 has changed. The change can be, it can be more than 100, or it can be less than 100, or it is different from 100. We call this as, let us say, the research hypothesis. Research hypothesis or alternate hypothesis. Or we can represent by H1, or some books give it as HA, alternate. Are you with me? Are you able to follow it? So we were having a situation where our average normal daily sales used to be $100, and based on the circumstances, you may feel that one of the three things can happen. You may feel that the average daily sales has increased, or it is decreasing, or it is different from your $100. So your $100 was your status quo. Are you with me? Or we call it as the null hypothesis. Are you with me?
Doctor, what's null hypothesis?
The null hypothesis is your status quo. That is the status of the organization or the status of the parameter.
Okay.
You can represent it by H0 or sometimes by Hn, null, H null. Generally we will call it as H0. H0 is the status quo and H1 is the research hypothesis. Are you with me? Is
Yes.
it clear? So you want to see whether the mean has improved or whether it has deteriorated or whether it has changed. So that we call it as H1 or the alternate hypothesis, and the original situation, the mean was $100, we call it as the null hypothesis. Generally what we say is the null and alternate hypothesis, they are mutually exclusive and exhaustive. And we consider H1 as an opposite of H0 or H0 as opposite of H1. They are complements. We take H0 and H1 as complements or complements or opposites, you can say. They are mutually exclusive and exhaustive. When I say that mu is greater than 100, generally I can write the opposite of mu greater than 100 as mu less than or equal to 100. Even that is considered as a null hypothesis. The opposite of greater than 100 is less than or equal to 100. Are you with me? And the opposite of mu less than 100, I can call it as mu is greater than or equal to 100. And the opposite of mu not equal to 100, I can take it as mu is equal to 100. Generally, these three are considered as H null or H0, null hypothesis. And these three are considered as H1, alternate hypothesis. Are you clear? Are you with me?
Yes, clear.
So you want to see at a time, what is your research hypothesis? You want to test. You want to test the hypothesis, whether the mean has increased or whether the mean has decreased or mean is different from the original status quo, the value which you were having earlier, any value. It can be 100 or 1000 or 1 million or 2.5 or 3.9, anything. Any value, let us say mu equals some given value mu 0. Mu 0 is a constant. You can call it as mu is equal to mu 0. So the alternate is mu is greater than mu 0, mu less than mu 0, mu not equal to mu 0. So these are the three situations which you can come across. At a time, you will come across only one of them. The situation can be mu is greater than 0, or you are testing for mu to be less than 0, less than mu naught, or you are testing for mu to be different from mu naught. Are you with me? Is it clear?
Yes.
So in a given problem, you will be having either H0 or H1. You may get H0 or H1. When once you are given H0, the opposite of H0 is H1, the opposite of H1 is H0. You must be able to write down the other hypothesis also. Is it clear? The average daily sales used to be $100, and the manager of the shop feels that the average has increased, or there is an improvement in the daily sales average. So in those situations, what is given? Mu is greater than 100. So you must be able to look for the catchword in the question, and you must be able to write down. Are you clear?
Yes. So H1 is the alternative.
So alternate is H1 and null hypothesis is H0. How do you identify H0 or H1? How do you say that a hypothesis is null or alternate?
I believe if there is assumption more than the mean or or not equal the H0, it will be H1.
Okay, here we have got a thumb rule which you must always remember. Note that in H0, the common thing is equality, equal sign. Are you clear? Wherever there is equal sign, it is always H null, H0. Are you with me?
Okay.
So H0 has got equal sign. H0 has got equal sign. So wherever there is equality sign in the hypothesis, it is the null hypothesis. So where there is, note that in the alternate hypothesis, it is strictly greater, strictly less, or not equal to. So if you come across strictly greater or less or not equal to, where there is no equality sign, it is always H1. And the null hypothesis always has got equality sign. So please remember that. So in any question, either you can get H0 or H1. If you are given H0, write down the opposite of H0, it becomes H1. If you are given H1, write the opposite of that and it becomes H0. So the first thing you have to do is determine the null hypothesis and the alternate hypothesis. That is your first step. Are you clear?
Yes.
So your first step in your hypothesis testing is define H0 and H1. So write down the hypothesis based on the question you are given. So look for the sign. If the sign doesn't have the equality sign, then it is alternate hypothesis. If the sign has got equality sign, then it is the null hypothesis. So look for the catchword: improved, deteriorated, different from. as much as. So like that, there will be the words. So which means that there is a, which gives you an idea about what is the type of inequality which you have got. If it is strict inequality, then it is H1. If there is equality sign, then it is H0. So write down the hypothesis based on the question and write down the opposite of that. Look for the hypothesis where you have got equality sign, put it as H0, the other one becomes H1. H1 will never have your equality sign. Are you clear? Are you with me?
Clear.
Okay. So then what will you do? How do you test? Let us say I want to see that the average has increased. Say for example, I want to look for situation 1. The average sales is more than 100. So how do you test it? The best way is by taking a sample, isn't it? Take a sample and based on the sample, you will arrive at your mean and see whether the mean is away from 100 or not. Are you with me? Is it clear?
Yes.
Okay. Yes. So I take a sample of size n, let us say, and based on the sample, I arrive at the mean. Let us say my alternate is true. H1 is true. Actually, the mean is greater than 100. Then where will be my mean? Where will be the X bar? The mean based on the sample. If H1 is true, I know that actually the sales are more than $100 daily sales. So what will be the value of X bar? Will it be more than 100 or less than 100? Naif?
Yes, doctor.
Did you get my question?
Can you repeat again?
I want to test whether the mean is more than 100, the first situation, okay?
Yes.
And I know that it is true, H1 is true, means it is actually more than 100. When H1 is true, and if I take a sample and calculate the mean, will the mean be generally more than 100 or less than 100?
Okay.
More than.
Will it be more or less? I know that H1 is true.
Of course, more.
It should be more, isn't it?
Yes.
So because I know that H1 is true, mu is more than 100, so my value of this X bar will be somewhere on the right side. Are you with me?
Yes.
So this is where the value of X bar will be there, so that I can say that H1 is true, or I can say that H0 is false, or I can say that you reject my H0. Are you with me?
Yes,
Because H1 is true, I reject H0. Yeah?
Yes, clear.
Okay, so this is my situation 1. So when I have got this situation 1, so the mean may be 100, but when once I know that H1 is true, the value of X bar will be somewhere on the right side. So on the right tail, I have got the rejection region. So we reject H0 and we call it as the rejection region. Or sometimes it is called critical region. With me?
Yes.
Rejection region or critical region where I am rejecting my null hypothesis will be on the upper tail, on the right side. Are you with me?
Yes.
Now, let us say I come to second situation where mu is less than 100 and I know that H1 is true. Then how does where will be my rejection region?
On the left.
On the left side. So the value of X bar will be on the left side. So my rejection region, because I know that H1 is true, So mu is actually less than 100. So my rejection region will be on the left side. If I look at the third case, and if I know that H1 is true, where will be my rejection region?
All of them.
H1 is true means it is different from 100. It can be more or less. Are you with me?
Yes.
So we reject null hypothesis whether it is more or when it is less. On both directions, we can reject it. Very clear?
Yes.
So the rejection region will be on two areas. So this is my second situation and this is my third situation. Very clear?
Clear.
So note that in situation 1 and 2, I have got rejection region either on the upper side, upper tail or lower tail, only on one tail. Whereas in situation 3, I have got the rejection region on two tails, both upper and the lower tail. Are you with me?
Yes, clear.
So because the rejection region is only on one side for 1 and 2, situations 1 and 2, I call it as one tail test. Situations 1 and 2, where I have got rejection only on one direction, I call it as the one tail test. And situation 3, which is not equal to, we call it as the two tail test. Are you with me? Is it clear?
Yes, clear, Doctor.
So how to identify whether it is one tail or two tail? Look at H1. Look at H1 and look at the sign. If it is strictly greater or strictly less, it is one tail test. If it is not equal to, it is a two tail test. So the second step we can say in your hypothesis testing is see whether it is one tail or two tail. Define or identify, let us say, identify one tail or two tail test. Are you with me?
Yes, clear.
So how do you do that? Look for H1, and if H1 is not equal to type, it is a two tail test. If it is strictly greater or strictly less, it is one tail test. If it is strictly greater, the rejection is on the higher side. If it is strictly less, the rejection is on the lower side. So what we can do, define H0, define H1, look at H1 and see whether it is a one tail test or a two tail test. Then draw a graph and put where the rejection region is. If it is strictly greater than type, we have got the rejection on the right side. If it is strictly less than type, the rejection is on the lower tail. If it is not equal to type, the rejection is on both the tails. Are you with me?
Yes.
Okay. The rejection region, the point beyond which there is rejection region, or beyond which we have got the critical region, this particular point we call it as the critical value. We call that particular point as critical value. With me? Let us say CV. So the point beyond which we reject the null hypothesis is the critical value. There is one critical value for one tail test. So this is the critical value for one tail test. And in the case of two tail test, we have got two critical values. Are you clear?
Yes.
Because we will reject it on both tails. Are you with me? Any questions?
I believe it's clear.
Okay. Now, the decision is made based on taking the sample. So under the null hypothesis, we know that the mu is equal to 100 and we are trying to test whether mu is greater than 100. By taking a sample, we are seeing whether the value is in the critical region, that is beyond the critical value on the upper tail. If it is beyond critical value, we said we are rejecting null hypothesis. Otherwise, we do not reject the null hypothesis. So if it is below that, we do not reject null hypothesis. Yeah?
Doctor, I get one question. Now,
Yes.
on the case, I think on the bottom right,
Yes.
we are testing mu equal 100 or mu not equal 100. Which one is it?
Yes. Mu equal 100 is your null hypothesis. H naught is mu equals 100 and H1 is mu not equal to 100. This is for case 3.
Okay, so which one we are drawing on the bottom right? Which one we are drawing?
Here I am looking at the mean. This is third case, okay? Are you with me?
I didn't.
So I am looking at the mean somewhere here, and let me say if H1 is true, means mu is actually different from 100. Means the value based on the sample will be either on the lower side or it can be on the higher side. In both these situations, we are rejecting our null hypothesis.
We are rejecting mu equal 100, right?
Yes, we are rejecting mu equals 100 and we conclude that mu is different from 100.
Okay, then why the rejection area is
Yes.
not everything but the red line in the middle?
The line in the middle is the mean. Don't worry about that. So in between these two, we are accepting null hypothesis. Are you clear?
So this is all 100? No, 100 needs to be one single line, not a region.
In this region, if the value of x bar lies within this region, within the two critical values, then we can say that there is no significant change in the value of mu from 100. It is still 100. Means we can still go with our null hypothesis. Whereas if it is very far from the mean, then we can say that it is different from 100. Did you see the logic?
So you are saying everything between the two rejection areas
Yes.
is mu equal 100?
Yes, there is, because there could be errors due to sampling. Error due to samples. We are taking a sample and just now we have seen there is sampling error. Z sigma by root n.
Mu equal 100 is one single line, not a region, Doctor.
No, it is a hypothesis. I am coming to that. I have not yet given the total picture. Okay. I am trying to give you some justification or the logic behind the development of the hypothesis testing.
Okay.
Are you with me? I have not given you the full picture.
Okay, clear.
So we are bringing in the probabilities now. We will bring in the probabilities. Now what I am telling initially is that by looking at H1, we must be able to identify whether it is one-tail test or two-tail test by drawing the graph and seeing the rejection region. The rejection region will be on one side or both sides. It will be on one side in case 1 and 2, that is strictly greater or strictly less than mu naught. And it will be on both sides if it is not equal to type. Very clear? Hisham?
Yes, clear. Yes,
Okay,
clear. Thank you.
I am only stopping here now. Okay. Now, the decision is made based on a sample. So there are sampling errors which are coming into the picture. So we can go wrong when we are taking a decision. Are you with me? Is it clear?
Mm-hmm.
So we can go wrong. What can what are the things where we can go wrong? We can reject a true hypothesis. Reject H naught when it is true. Are you clear? Are you with me?
Yes, I'm
It
with
is a
you.
mistake.
Meaning that, yeah, your sample wasn't correct.
Yes. So based on the sample, we are arriving at a decision which is a wrong decision. So where though there is no change in the mean, or though there is no change in the distribution pattern, we are telling that the mean has changed. It can be more or less or not equal to. Means we are rejecting our null hypothesis when actually it was true. Are you with me?
Yeah.
This we call it as the type 1 error. And we represent this by alpha. It is nothing but our level of significance. Are you with me? Is it clear?
Yes.
When we reject a true hypothesis, we are committing a mistake. That mistake we call it as type 1 error, and we call it as the level of significance, that is alpha. Or we can commit another mistake. What is the other mistake? Accepting a false hypothesis. Accept H naught when it is false. Are you clear? Are you with me? This we call it as type 2 error. We call it as beta. Is it clear?
Yes.
So we can commit two types of errors. Rejecting H naught when it is true, we call it as alpha, or accept H naught when actually it is false. So we call it as type 2 error or beta. And one is called the power of the test. 1 minus beta is generally, we call it as the power of the test. What is 1 minus alpha? What is 1 minus alpha? Just now I have been telling in the last chapter.
The confidence.
Confidence.
Level of confidence. 1 minus alpha is the level of confidence, and 1 minus beta is the power. Alpha is type 1 error and beta is type 2 error. Type 1 error is rejecting the null hypothesis when it is true, and type 2 error is accepting the null hypothesis when it is false. Note that we cannot control both. If we try to reduce alpha, beta increases. If we try to reduce beta, alpha increases. Are you with me?
If we
So we
increase
cannot
alpha,
control
what?
both. If we want to reduce alpha, beta increases. If we want to reduce type 1 error, type 2 error goes up. If we want to reduce type 2 error, type 1 error goes up.
Oh, okay.
So we have to make a balance, or we have to fix one. So generally the hypothesis testing procedure is based on fixing alpha. So we fix alpha and we develop our procedure. Are you clear? We fix alpha. Are you with me? Are you clear?
Yes.
So what is alpha? Alpha is nothing but this area where we are rejecting null hypothesis, though the distribution is same. So this is nothing but our alpha, this area. The critical area, the rejection region is alpha. Are you clear? That is our type 1 error. If we say alpha is 5%, we are rejecting a true hypothesis 5% of the times. In other words, we are committing a mistake 5% of the times, or we are right 95% of the times. Similarly, if you are in situation 2, what is alpha? The area below the critical value. This is alpha. Are you with me? The rejection region. And in case 3, what happens? Alpha is distributed in 2 areas. So it becomes alpha by 2 and alpha by 2 on both sides. Are you clear? Are you with me?
Yes.
So now what is our next step? Define H0, define H1. Identify whether it is a one-tail test or a two-tail test. Now, third one is fix alpha, define alpha. Alpha is your level of significance. If it is given in the question, take it as it is. Say 2%, 5%, 10%, whatever. If nothing is given, you can take it as 5%. Are you clear? 5% if nothing is given. If it is not defined, you can define it. 5% is alpha, means you are committing mistake 5% of the times. Means 95% of the times you are arriving at a right decision. Are you with me? Is it clear?
Yes, doctor.
So when once you fix alpha, now you take a sample and see whether you are using a test statistic which is using the distribution which we use. We make use of our central limit theorem, where we know that x bar follows a normal distribution when sigma is known. We use the z distribution. If sigma is unknown, we use a t distribution. So if we use the z distribution, we get the critical value from the z table. And what is our critical value? The critical value will be z alpha. Z alpha for case 1. Are you with me?
Yes, the rejection region.
The rejection region. The critical value will be Z alpha, and for case 2 it will be minus Z alpha. Clear? And for case 3 we have got plus or minus Z alpha by 2, because the area beyond the critical value is alpha by 2. So there will be 2 critical values, plus Z alpha by 2 and minus Z alpha by 2. Are you with me? So when once you define your alpha, you are looking at the tables and getting your next step. Get the critical values. Get the CV. Critical value from tables. Is it clear?
Yes.
Now you have got a critical value, and we make use of the sample which we have got, and we calculate what is called the test statistic. So this step number 5 is calculate test statistic. Test statistic is a formula. What is the statistic? It is nothing but our z, x bar minus mu by sigma by root n, when sigma is known. If sigma is not known, we use t. So it will be x bar minus mu by s by root n, and we get the critical value using this t table. It will be t alpha or t alpha by 2 with n minus 1 degrees of freedom. In case of proportions, if np and nq are greater than or equal to 5, we can still use our z distribution. So z will be p cap minus p by root pq by n. The same formula will be our test statistics. So based on the sample you have collected, calculate x bar, use the value of n, If sigma is known, use Z. If sigma is unknown, make use of S for sigma. The formula for T becomes x bar minus mu by S by root n. For case of proportions, if NP and NQ are greater than or equal to 5, we can make use of the Z distribution, the test statistic being P cap minus P by root PQ by N. So this will be our test statistics. So we calculate the test statistic, either Z or T. Are you clear?
Yes.
Now we compare the calculated value of the test statistic with the critical value obtained from the table. So if the test statistic value is below the critical value, then we do not reject our null hypothesis. If it is in the critical region, we reject the null hypothesis. Are you clear? So the final step, number 6, let us say, is compare the statistic with critical value and arrive at decision. What is the decision? If it is in the critical region, reject H naught. If it is not in the critical region, do not reject H naught. Are you with me?
Yes. Yes.
So these are the steps in our hypothesis testing procedure. So define H naught and H1 by looking at H1, see whether it is one-tailed test or two-tailed test. Define alpha. If it is given in the question, use that value of alpha. If it is not given, you can take it as 5%. Now look at the situation. If it is the case of means, if sigma is known, then you look for our Z table and get the critical value, because the test statistic will be Z, x bar minus mu by sigma by root n. If the sigma is not known, if you are making use of small s, that is your sample standard deviation as an estimator for sigma, then make use of the T distribution. So the formula for T will be x bar minus mu by S by root n. Then you have to use your T distribution table with n minus 1 degrees of freedom. If it is for the proportions, NP and NQ, if they are greater than or equal to 5, you can go for your Z distribution, and the test statistic will be P cap minus P by root PQ by N. So once you calculate your test statistic, compare with your critical value. And if the test statistic is in the rejection region, reject H naught. If it is not in the rejection region, do not reject H naught. For one-tailed test, there is only one rejection region. For two-tailed test, there will be two rejection region. Is it clear? Any questions?
So alpha, if it's not given, we will take it as 5%, right?
5%. Yes, you define it as 5%. Take it as 5%.
Okay.
Okay. So these are the things which are given in our initial slides. Shall we go to slides quickly?
Just 1 minute, Doctor. I'm
Yes,
writing
please.
notes.
So you can say the main steps 1, 2, 3, 4, 5, 6. These are the steps. You can say these are the main things which you have to carry out for hypothesis testing. These 6 are in detail, elaborate steps. Is it clear? Shall we go through the slides?
Doctor, step number
Yes.
6.
Number 6, compare the test statistic, that is your calculated value, Z
Yes.
or T, okay, with the critical value, which you have got from the tables. critical value you get using the table, either Z table or T table.
Yeah.
So if it is, if the test statistic value is in the rejection region, it is beyond your critical value, then you reject your null hypothesis.
Oh, okay, okay.
Okay. If the value of the test statistic is in the critical region, that is, if it is beyond your test statistic, the critical value, then you reject your null hypothesis. Otherwise, do not reject your null hypothesis. That is the decision. Is it clear?
Clear,
Can
yes.
we, Doctor, get one example, please, so that we can apply?
Yeah. We will go through example. We will go through example. In the slides, it is given. So these are the steps to get an idea about the procedure. Okay. So only when you are clear about this procedure, we can apply this procedure for the example. That makes it more clear. Okay, let us go through the slides. Okay, can you see this? Can you see this slide? Osama?
Yes, I can, yes.
Okay. Statistical hypothesis testing is a means of assessing whether apparent results in a sample conclusively indicate that something is really happening. So we are taking a sample, and based on the sample, we are arriving at a decision whether something really is changing, whether mu is strictly more or less or different. So whether there is any change which is happening in the distribution. So it serves to check how strong the evidence is. So the evidence is the sample. So based on the sample, we are trying to arrive at a conclusion for the parameter of the population. So there are four major components: the null hypothesis, alternate hypothesis, test statistic, and the rejection region. I hope you are clear about this. So a research hypothesis typically states that there is a real change or a difference or a real effect in the underlying population process. So this is our research hypothesis, which we call it as the alternate hypothesis. And the null hypothesis states that there is no real change or difference or the effect. So we say that status quo is maintained. So that is our null hypothesis H0, and the research hypothesis, which says that there is a real change. This is our alternate hypothesis. So these are some of the examples. Null hypothesis always has equality. It may be less than or equal to, or greater than or equal to, or equal to. Okay, the null hypothesis specifies that the parameter is equal to a single value. For one-tailed test, it may be greater than or equal to or less than or equal to type. So let us look at an example of the null hypothesis. Is the average daily wage for this particular subpopulation is equal to normal average, say $7.5. So our null hypothesis says mu is equal to 7.5. Is it clear? So it is equal to, means it is a null hypothesis. Or it can be the alternate hypothesis, where it says that the parameter can be of one of the following. It can be greater than type, where we say that mu is more than 7.5. Very clear? It is more than type. Or it can be less than type, where mu becomes less than 7.5. So whether it is less than type. So this is another type, mu is less than 7.5. Or whether the average, it is different, means it is not equal to 7.5. So mu is different from 7.5. So these are the three types of alternate hypothesis we can have: strictly less than, strictly greater than, or not equal to. So some of the things which you can remember: H0 is null hypothesis and H1 is the alternate hypothesis. H0 and H1 are mutually exclusive and collectively exhaustive. H0 is always presumed to be true and H1 is our research hypothesis. So we take a sample of size n and we make use of this either to reject H0 or do not reject null hypothesis. If we conclude do not reject H0, it means that it is not always meaning that the alternate is true. There are chances that you can go wrong. So that chances of going wrong is your alpha, the type 1 error. Okay. Equality is always with your null hypothesis. And not equal to or strictly less or strictly greater is the part of H1. So in practice, the status quo is set up as H0. And in problem solving, look at these keywords and convert them into symbols. Let us say improved, better than, as effective as, different from, has changed. So all these are keywords. Improved means maybe greater than, better than, maybe strictly greater than, as effective as means equal to, different from, not equal to, it has changed, not equal to. So look at some of the things which can happen. Say at least, let us say greater than or equal to. Has not changed means equal to. No more than, less than or equal to. So if there is equality, it becomes H0. If there is no equality, it becomes H1. Very clear? So look at these catchwords and write down the hypothesis. Yes, please. Is it clear, Mr. Osama?
Clear, yes.
Yes. Okay, when we look at the sign, the symbol for H0, the signs for H0, for a two-tailed test, it will be equal to against not equal to. So there will be a rejection region on both tails. If it is strictly less than, the H0 could be equal to or greater than equal to, and the rejection will be on the left side. And if the alternate hypothesis is strictly greater than, then H0 can be equal to or less than or equal to, and the rejection will be on the right side. So we have got two situations where there is rejection only on the one side, and one situation where there is a rejection on both sides. Because there is rejection on only one side, we call the left tail or the right tail test as one tail test. And this is a two tail test. Very clear? Graphically, if you want, you can see if the rejection is on both sides, then we have got a two tail test. And if the rejection is only on one side, then it will be at the one tail test. So here alternate is strictly less than, here alternate is strictly greater than. Here the alternate is not equal to. Very clear? Are you with me? Shall we proceed? Same thing which we had explained earlier. Shall we proceed? Naif?
Yes.
Okay. Yes. Okay. So as I told you, there can be two types of errors where we'll be rejecting H0 when actually it is true. So we call it as type 1 error and represent by alpha. Or you do not reject H0 when it is false. So we have got type 2 error, we call it as beta. Alpha is called level of significance and 1 minus alpha is called the level of confidence. Beta is our type 2 error, 1 minus beta is called the power of the test. So the purpose of the test is to determine whether it is appropriate to reject or not to reject our null hypothesis. Therefore, the test statistic is the sample statistic upon which we base our decision. So we make use of the test statistic, which is nothing but the formula, either to reject or not to reject our null hypothesis. And what is the rejection region? The area where if the test statistic falls, we call it as a rejection region, and if the test statistic is in the rejection region, then we reject our null hypothesis. So since the conclusion we are drawing is based on sample data, the chances of our making one of the two possible errors will always exist. That is alpha and beta. So here once again you are given what is the hypothesis, what is the hypothesis testing, which is a procedure based on sample evidence and probability theory to determine whether the hypothesis is a reasonable statement. Then you know what is the test statistic, and you know what is the critical value, and maybe you can say these are the steps. State the null and alternate hypothesis H0 and H1, select alpha, the level of significance, identify the test statistic, formulate a decision rule. So what is decision rule? Look at your critical value from the tables. Take a sample and arrive at a decision. So using the sample, calculate the test statistic and compare with your critical value. So two outcomes can be there. Do not reject H0, or reject H0 means accept H1. Is it clear? Does it make sense? One sir?
Yes,
Naif?
yes.
Hisham? Okay.
Yes.
So what is test statistic? As you know, the test statistic is nothing but the formula we use. So the test statistic, in case of when sigma is known, the Z statistic will be x bar minus mu by sigma by root n. If sigma is not known, we use the T statistic, x bar minus mu by s by root n. In the case of proportions, we use our Z statistic. Okay, don't worry, this you can change it. P cap minus P by root PQ by n. Some books they give it as pi and P. Pi for the population and P for the sample. Okay. So you can we use the notation P cap minus P by root PQ by n. So depending on the situation, whether sigma is known or unknown, for testing for the mean, we use either Z or T distributions, and for the proportions, if NP and NQ are greater than or equal to 5, we use the Z distribution. P cap minus P by root PQ by n. So these are the steps you can say. Define H0, define H1, calculate test statistic, determine the rejection region, compare the value of test statistic with the critical value, and arrive at a decision. I have given you more details. Define H0, define H1, look for whether it is one-tailed test or two-tailed test, draw a graph to arrive at the rejection region, mark the rejection region, then define your alpha, get your critical value from the tables, either Z table or T table, then calculate your test statistic using the formula and compare your value of the test statistic with the critical value and arrive at the decision. Is it clear? Does it make sense? No response.
Clear.
Clear. Okay. So let us look at an example. Things will be more clear. Jamestown Steel Company manufactures and assembles desks and other office equipment. The weekly production of model A325 desk, some model, okay, at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. So you are given mu and sigma. Recently, new production methods have been introduced and new employees were hired. The mean number of desks produced during the last 50 weeks was 203.5. The Vice President of the Manufacturing would like to investigate whether there has been a change in the weekly production of the model A325 desks at 1% level of significance. Is the problem clear?
Yes, clear.
So you are manufacturing a product, some A325 desks. So the mean used to be 200 with a standard deviation. Mu is 200, sigma is 16. Clear?
Yes.
So you are giving some new methods of manufacturing. So after that, you took a sample for 50 weeks, and the sample mean used has come to 203.5. So as the Vice President, you want to see whether there is a change in the weekly production. Change means, that is the catchword.
Not equal.
So you want to see whether there is a change. Mu is What is hypothesis?
Mu not equal 200.
Not equal. Not equal. Change means different from. So mu is not equal to 200. So that is your catchword. So based on that, you are writing your H1. So mu is not equal to 200 is what you get from here. So the opposite of mu not equal to 200 is mu equal to 200. So equality means that becomes H0, not equal to becomes H1. So because it is not equal to, it becomes a two-tailed test. Very clear?
Yes.
So draw a graph and look for two critical values. That is two rejection regions. Because it is not equal to, there are two dark areas. So these are the rejection regions where you reject your null hypothesis. Now alpha is given to be 1%, means 0.01. So it is given. So you have to consider it as 0.01 only. So look for alpha 0.01. So what is your next step? Get your critical value. You have to use your Z distribution because sigma is known. Are you with me?
Yes.
So because sigma is known, you use our Z distribution. So you look for your rejection alpha by 2 areas beyond in the rejection levels, isn't it? So this will be your alpha by 2. So look for the two critical values based on your area beyond the critical value. So alpha by 2 becomes 0.005. So if this is 0.005, then you can get your critical value using your Z table. Are you clear? So if that is 0.005, what is the area between 0 and Z? Between 0 and Z, it will be 0.495. So look for the area 0.495 in the table and get your Z, the critical value, that is your Z value from the table. It will be 2.58. Can you check it? Are you getting it? Mansur, South, Osama?
1 minute, Doctor.
Yeah. Look for the area 0.495.
0.495.
Because alpha by 2 is half of 0.1. So it will be 0.005.
Yes, it's 2.5. 8 or 7.
7, okay. So here it is taken as 2.58, okay, doesn't matter. So the critical values are plus 2.58 and minus 2.58. Z alpha by 2 and minus Z alpha by 2. This you are getting from the table. Are you clear? Are you with me? Then calculate your test statistic. Yes? Any questions, please? One, sir?
No, clear.
Yeah. So what is your next step? Calculate your test statistic. What is your test statistics? X bar minus mu by sigma by root n. You know X bar 203.5, mu is 200, sigma is 16, and n is 50. Substitute the values and simplify, you will get 1.55. Are you clear? Are you with me?
Yes.
So now compare this 1.55 with your critical value. 1.55 with 2.58. Is it less than 2.58? Yes. So 1.55 is below 2.58. So it is in the do not reject region, except H0. So do not reject H0. So because 1.55 is less than 2.58, we accept null hypothesis. And we do not accept the alternate hypothesis. So the null hypothesis says mu is equal to 200. So actually there has been no change in the weekly production now that it was used to be 200. Are you clear? So because 1.55 does not fall in rejection region, H0 is not rejected. We conclude that the population mean is not different from 200. So we would report to the Vice President of the manufacturing that the sample evidence does not show that the production rate of the plant has changed from 200 per week. So it has not changed. It still continues to be 200.
So the new production method and the new employees haven't changed the
They are not given any significant improvement.
Ah, okay.
Any significant change, rather. Okay. So that's how you carry out the hypothesis testing using the procedure of calculating the test statistic and using the tables for arriving at the decision. Are you with me?
Yes.
Okay, does this clarify better? Is it clear now? Shrisham?
Yes, thank you.
Okay. Now, okay, let us say I will slightly change now. Now, I have taken a sample of 50 weeks and the sample mean X bar happens to 203.5, isn't it? It used to be 200 and now it has changed to 203.5. So as a manager, I may feel that whether there has been an increase, instead of change, I will say that whether there is an increase, isn't it? Are you with me? I replace the word change by increase, whether there has been an increase in the weekly production. I can imagine, isn't it? It used to be 200, so for the last 50 weeks it has become 203.5, so it might be more than 200. Are you clear?
Yes.
Very clear.
So,
Doctor,
that, what happens? Yes.
in this case, it will be one tail test.
Yes. The entire thing changes. The alternate hypothesis will be more than 200. Are you clear?
Okay.
That is situation I am showing in the next one. So if I say that it is more than 200, then my situation becomes mu greater than 200, and the alternative, the opposite of that, less than or equal to, that is 200. So this becomes a one-tail test. Are you with me?
Yes.
So this becomes a one-tail test. So the rejection region will be only on one side. So the critical value now changes. The critical value will be Z alpha. Alpha is 0.01. This is one-tail test. So earlier, the critical value used to be 2.58, plus or minus 2.58. Now it has changed to 2.33. Very clear?
Clear.
Will the test statistic change? The value of test statistic? The formula is same. The values are same. So there is no change, isn't it?
Yes.
So the test statistic remains to be 1.55. So now you compare 1.55 with 2.33, because 1.55 is below 2.33. Again, we conclude that we accept H naught. Are you clear? It is in the acceptance region. H naught is not rejected. Do not reject H naught. So we still say that it is not more than 200. Are you with me?
Yes, clear.
Yes.
So by looking at the hypothesis, you must be able to identify whether it is one-tail or two-tail test, and then go ahead with your calculations and looking at your tables and comparing with the critical value, the test statistic, arrive at the decision. If the value was more than 2.33, we would have rejected our null hypothesis, because 1.55 calculated value is below 2.33. We will be not rejecting the null hypothesis. Is it clear?
Yes, very clear.
Okay. Now, let us proceed further and try to learn more. The calculated value of the test statistic. What was the calculated value? The calculated value is 1.55. Clear? Are you with me?
Yes, the same as before. Yes.
Yes. So what, can you tell me what is the probability of Z to be greater than this calculated value? Greater than 1.55?
Again, doctor.
Just a minute. Sir, I am in class. Sir, I am in class now. I will call later. So I have used the formula test statistic as x bar minus mu by sigma by root n. Are you with me?
Yes.
And the calculated value of the test statistic was 1.55. I am looking at the probability of Z to be greater than this calculated value, which I have arrived at using my sample. In other words, I am trying to find the probability of getting a sample which is as extreme, as more extreme than the sample I have got. Are you clear?
Yes.
So what is the probability of Z to be greater than 1.55? Can you tell me? Again, you have to use your table, isn't it?
Yes,
So
we take the complement.
Yes?
We take the complements of.
Yeah, you look for 1.55 area from 0 to 1.55 and subtract that from 0.5. So 0.5 minus the area from 0 to 1.55. Are you clear? So I am looking at this area, the red area.
So it will be 0.0835.
What is the value which you have got for 1.55 from the table?
At 0.4394.
0.4394. Okay. So 0.5 minus 0.4394. How much you will get? 0.0606.
0606, yes.
So the area beyond the calculated value, that is 1.55, is 0.0606. Is it clear to all?
Yes.
Now note that we have got alpha. This is the rejection region, 0.01 alpha. Clear? And now we have calculated the probability of Z to be more than the calculated value of the test statistic. That is the probability of getting a sample which is as extreme or more extreme than the sample we have got. This we call it as the p-value. Are you clear? We call this as p-value. 0.06 is the probability of getting a sample which is as extreme as the one which you have got or beyond. Are you with me?
Yes.
Isn't it Q value, doctor? Because it's
p-value, p-value. It is called p-value or the actual significance. Sometimes we call it, it is also called actual significance. Or just SIG value. Okay. So generally it is called the p-value. Are you with me? Is it clear? Yes or no?
Yes.
Yes. Okay. Now I can arrive at a decision rule by comparing p-value with alpha. Can I do that? Compare p-value with alpha. What will be your decision? The p-value is the area beyond your calculated value of the test statistic, and alpha is the area beyond your critical value. If the p-value is more than alpha, then you have got your test statistic in your acceptance region. Do not reject H0. In this example, 0606 is more than 01. Very clear? Are you with me?
Again, please, Doctor.
In this example, p-value is 0.0606. So if you compare 0.0606 with alpha, which is 01, 0.0606 is more than alpha.
Yes.
Very clear?
Clear.
0.0606 is more than 01. So that's why we say that we are accepting H0, let us say. Do not reject H0. Are you with me?
I have a question,
Yes.
Doctor.
Yes, please.
And to be honest with you, my problem is with step number 4. How did you translate the question into this statement, which is reject H0 if Z more than Z alpha?
Z alpha.
And in the previous slide, and in the previous slide, you did it differently. You put something very complicated.
Previous slide, what happened? In previous slide, what happened? You compared, this is your Z with Z alpha. Z alpha was plus or minus 2.58. There were two rejection critical values. Compare 1.55 with plus or minus 2.58. It is within these two values. So it is in the acceptance region, or do not reject H0. Okay? This was a two-tailed test. You remember, Hisham?
So is it always like this, which is the absolute value of Z more than Z alpha?
Yes, absolute value means plus or minus 2.58. The absolute value becomes minus 2.58 becomes plus 2.58. So if your critical value, if your computed value is beyond the absolute value of 2.58, that is if it is beyond, even if it is, let us say 2.9 or minus 2.9, in both cases, you are rejecting your null hypothesis.
So always, if it is two-tailed, we go with the absolute value of Z.
Absolute value. So that's what I have given here, isn't it? So that's what I have given here. I hope you have got some confusion here, isn't it? Absolute value greater than Z alpha by 2. It can be absolute value. When I say Z alpha by 2, it can be plus or minus. So you are looking at the absolute value. So in this case, let us say in this example, when you are looking at the two-tailed test, the absolute value of 1.55 is still 1.55. Even if it was minus 1.55, it will be 1.55. So even then, we'll be in the acceptance region.
Okay, clear now, clear.
Yeah?
Thank you.
So two values are made plus or minus. It is represented as absolute value there. That's all. Okay? Does it clarify your doubt?
Yes, clear, inshallah.
Okay. So let us come back to our p-value. The p-value in this example happens to be 0.0606. So we are seeing that the p-value is more than alpha. So our decision is accept H0.
And if the p-value is less than or equal to alpha, then it will be in the rejection region. So we'll be rejecting our null hypothesis. Are you clear? Are you with me?
Yes.
If p-value is less than or maybe equal to alpha, then reject H0. So this is our decision rule. Are you clear? So if you can get the p-value, then just compare your p-value with alpha. Alpha is given or you have defined it as 0.05, whatever it is. So just compare p-value and alpha and arrive at the decision. So in most of the softwares, we get the p-value. That is the advantage. So when you go for the software, in the output, it gives the p-value. So when you have got the p-value, you just compare the p-value with alpha. If the p-value is less than alpha or equal to alpha, reject H0. If it is more than alpha, you do not reject H0. Are you with me? What is the advantage? We need not have the test statistic. No need to look for the formula. We need not have the tables. Whether it is Z table, T table, whatever table, we need not have our tables. We need not have our critical value from the tables. We are just comparing the probabilities. We are comparing the p-value with alpha. Look for your p-value in the output. Compare with alpha. If p is more than alpha, do not reject H0. If it is less than or equal to alpha, reject H0. Are you with me? The life becomes more simple. Is it clear, Mr. Abdul Majid? This question for everyone. Is it clear?
Yes, clear.
Okay. So what will be our testing procedure now? Define H0, define H1. Look whether the alternate hypothesis, whether it is one-tailed test or two-tailed test. Define alpha and look for your p-value from the output of the software. Now, if it is a two-tailed test, we look for the actual significance. Generally, what happens is the actual significance is given for two-tail. In the output, it gives SIG value two-tail. Are you clear? The output generally gives SIG value two-tail. Gives us two-tail. So if it is a one-tail test, that is your p-value. For one-tail test, you take half of p, you divide it by 2 and compare with alpha. Are you clear?
Doctor, for the p-value, we mean area under the curve, right?
Yes, it is a probability.
Yes, but here in probability of z bigger than 1.55,
Yes.
it will be the area that include the rejection region.
Yes. So it is the area which is including, which is beyond our sample statistic. The rejection region is the area beyond 2.33, which is 0.01 alpha. The rejection region is 0.01 area. And based on the sample, we got the p-value to be 0.0606.
Yes.
If the value which you had got instead of 0.06, if I had got 0.006, then it will be less than 0.1, it will be in the rejection region. Are you clear?
Yes, clear.
So smaller the value of p-value, larger is the chances that alternate hypothesis is true. Are you with me?
Yes.
Say, generally what we say, if p-value is less than 1%, we say there is a very high chance, overwhelming evidence that H1 is true. If the p-value is between 1 to 5%, then we say there is a strong evidence that alternate hypothesis is true. If it is between 5 to 10%, there is a weak evidence that H1 is true. And if it is more than 10%, we say there is no evidence that H1 is true, so we accept H0. So that's how we interpret our p-value. Smaller the p-value, greater are the chances that H1 is true.
Okay.
Is it clear?
Yes, clear.
So get the p-value from the table, from the output of the software, like SPSS. So compare your p-value with alpha, and if p is less than alpha, then you reject your null hypothesis. If it is greater than alpha, do not reject your null hypothesis. If it is a one-tailed test, you compare p by 2 with alpha. You compare p by 2 with alpha because it is only on the one side. So compare p by 2 with alpha, and if p by 2 is greater than alpha, accept H0. If it is less than or equal to alpha, reject H0. Very clear?
Yes, clear.
So that is the procedure which we will be adopting when we make use of our p-values and when we use our software. The advantage of this is we need not bother about formula. The formulas becomes more and more complicated if we go for different methods of testing of hypothesis. So we need not go for all these calculations. We need not make use of the tables. We also see that we will have different distributions. It need not be Z or T. We will have F distribution, chi-square distribution, different distributions. So we need not bother about all these distributions. We just look for the p-value from the output, compare it with alpha. If p is less than alpha, reject H0. Otherwise, do not reject H0. That is our rule. Are you clear? Is it clear to all? Yes, Mishman sir, is it clear?
Yes.
Yes, clear.
So what is the p-value? As we have seen, the p-value was 0.0606, which is nothing but the probability of Z to be more than 1.55, which is our calculated value. So this is our p-value. Compare p with alpha. So the decision rule is reject null hypothesis, reject H0. This is our decision rule. Reject the null hypothesis if p is less than alpha. Otherwise, do not reject our H0. So the p-value is the probability of observing a sample value as extreme or more extreme than the value under observation given the null hypothesis is true. So in testing of hypothesis, we can compare p-value with alpha, and the decision rule in this case is reject null hypothesis if p-value becomes less than alpha. Is it clear? So as I have told you, smaller the p-value, greater is the evidence that H1 is true. If p-value is less than 1%, there is overwhelming evidence that the H1 is true. If it is between 1 to 5%, there is a strong evidence. And if it is between 5 to 10%, there is a weak evidence. And if it is more than 10%, there is no evidence that alternate hypothesis is true. Is it clear? Anyway, okay, 1 minus beta is called the power of the function, power of the test, which we have seen already. And these are the steps in hypothesis testing using the software SPSS. State the null H0 and H1, see whether it is one-tailed test or two-tailed test, define alpha, calculate the actual significance or the p-value, read it from the output, make a decision. What is the decision rule? Reject H0 if p is less than or equal to alpha for a two-tailed test. For a one-tailed test, you compare p by 2 with alpha. So reject H0 if p by 2 is less than or equal to alpha for one-tailed test. That is your decision. Are you with me? Is it clear?
Clear.
So this is the procedure which we follow when we are making use of our software. Please note that though we are using p-value, actually what we are doing is we are carrying out the entire procedure. We are not explicitly using the formula, we are not calculating the test statistic, we are not making use of the table, but the software would have done all those things. To arrive at the p-value, it would have taken care of all these things and it will give you the answer. So just look for your p-value, that is your SIG value. So sometimes it will be called as the SIG value, actual significance. SIG, or sometimes even two-tail. SIG two-tail value. Clear? From SPSS output. So look for your SIG two-tail value from SPSS output. That is your actual significance, and compare that with your alpha. Are you clear? So most of the times we'll be looking at use of the software when the sigma is unknown, because most of the situations we'll be taking the sample and based on the sample we'll be calculating the mean and sample standard deviation. So using sample standard deviation, what we have to do? We have to make use of the t-statistic. So we use the t-statistic when sigma is unknown. So when sigma is unknown, we make use of the t-statistic, and the formula for t-statistic will be x bar minus mu by s by root n, where n is our sample size and the degrees of freedom will be n minus 1. So using the t-statistic and using the t-table, we can carry out the test of hypothesis, or alternately, we can make use of the software and we can see how convenient it will be to look for your p-value and compare p with alpha and arrive at a decision. Okay? So you can make use of the software for arriving at the decision. Are you with me?
Yes, doctor. It's prayer time now. Can we stop here or we take a break?
Okay. Shall we stop here for today then?
Yes, please.
We will look for an example where sigma is unknown. Okay.
Okay.
And then
Okay.
we will see how to make use of SPSS. For the same example, we can see the difference as to how complicated it will be when you use your calculator or your traditional method, and how easy it will be when you use your software. Okay. So please go through this, be clear about the procedure using the tables and the formula, and the procedure using your p-value. So we can make use of an example and see how to use the SPSS software for arriving at the decision. Okay, we'll continue in our next class.
Okay, thank you, doctor.
Thank you, Doctor.
Okay, please, welcome. We'll meet again next week, same time, online. Okay?
Okay,
Thank
doctor,
you.
please
Bye-bye.
don't forget to upload the previous lecture on this lecture also.
The previous lecture,
Yes.
it is
on
already
this-
there, isn't it?
No, it's not.
It is. Okay, so let me check.
Yes, double check, please. And
Okay, I will double check and let you know. Okay?
thank you
Yeah.
so much. Thank you, doctor.
Okay.